to do, and let me do this. Yeah, so based on today's class, we're gonna be doing the inverse of trigonometric functions. So I think these are one of the questions that you're gonna be coming across on test 3. So let me start here. So what I'll do, right, I don't know if you guys have done this proof, but what I can do is the questions that can be asked usually it's these ones, right, where they tell you that if f of x is equals to, I think they say sine inverse x, and then f prime of x is equals to 1 over 1 minus x squared. I think for the arc sine it's like this, yeah. So they can tell you, they can say if f of x is equal to arc sine of x, then f prime of x is equal to this, and then they tell you to prove it. You see, right? So these are the type of questions that we're gonna be focusing on here. So if you can look at the previous question paper, you realize that these are the type of questions that they can ask. So when we come on this proof, they say that we're given a theorem that says in the open interval -1 and 1, y is equals to arc sine of x, and arc sine of x is differentiable and means that dy over dx will be equal to this, right? And then dy over dx will be equal to this. What is this doing? Yeah, dy over dx is equal to this. So now we are given that the interval is -1 and 1. We know that if we're going to bound any sign of something, maybe sign of x should be bound between -1 and 1. You see, right? So this is the bound that we apply for this. So now we say that for us to prove this, we are going to let y be equal to this arc sine x, given that x belongs, or x is an element of -1 and 1, or it's in between -1 and 1. And then from here we can introduce arc sine both sides. If I introduce not arc sine, if I introduce sine this side and the sine this side of arc sine y, hit this side is arc sine x, not y. This will be sine y is equal to x. You see, right? The arc sine will cancel the sine. So that's why we have this. Then x is equal to sine y. So now since we have that x is equal to sine y, we can now derive both sides. We can now derive, if I derive, you see, right? If I derive sine y, you know that I will get what? Cos y times the derivative of y with respect to x, which is equal to, if I derive x, I get 1, right? And then I divide both sides, I get 1 over cos y. You see, right? And then from here, you see we got what? We got cos y on the denominator. You agree, right? And then from here, we know this. We know something from grade 12. We know something that's sine squared x plus sine. Actually, since this is talking about not around sine, let me say y plus cos squared y is equals to 1. If I take sine to the other side, I'll have cos squared y is equals to 1 minus sine squared y. And then if I root both sides, I'll have cos y, and then I focus on the positive one. This will be 1 minus sine squared y. And what is sine y? Sine y is equals to x from there, right? So it means that cos of y will be equals to 1 minus x squared. You see, right? That's why we have this 1 minus x squared in the denominator, which is the same as this. So let's see what we have on the other side. I think I shouldn't be erasing this, it's fine. So if we see on the other side, we just changed that cos y to root of 1 minus sine squared y, which is this. Right? I showed you how did we find this. So given that we know that sine y is equal to x, so I just plug the x on sine y, then we get that. We can still do the same thing for tan. We can do the same thing for cos. We see that. Then now we look at the inverse cosine function. The inverse cosine function, the only difference that we'll have there is just this will be minus. That's right. This will be minus. So now this means that if we are given now this function, they say y is equal to, where's the thing of cancelling? Y is equal to cos, so it will always start here, right? We'll be given this. Let me write it somewhere here. Yeah, here's it. So for this theorem, they say that in the open interval -1 and 1, f of x is equal to cos or arc cos, right? And it's differentiable. If it's differentiable, means that the derivative of that will be this. The only difference, this one of arc sine and arc cos, they're the same. The only difference that the one of arc cos, we get -1 there. So how do you prove it? Since we are given that f of x is equal to arc cos, we're going to let f of x to be equal to y, and we'll replace x by y, where we know that x is in between that, -1 and 1. Then we introduce cos both sides, that we're going to be having cos this side to be cancelled, and then here we'll have cos y, which is this one, is equal to x, right? Then we derive both sides. We know that when we derive cos y, we get minus sine y. Then since we're deriving with respect to x, we'll multiply by dy over dx, which is equal to this side is 1. We divide both sides, we get this. And sine y, we get that this is, you know, sine y will be sine squared y plus cos squared y is equal to 1. Then we know we must make sine subject to the formula. Cos squared y, and we know that sine y is equal to root of 1 minus cos squared y. And we know that cos is equal to x. We substitute x there. You see, right? Then we get -1 over root of cos -1 over root of 1 minus x squared. Then we get that. So do we agree on this? Now for this, now we come to definition 6.11. Now we look at the tangent function. I think last year they brought the one of tangent. This year they can bring any between arc cos and sine arc sine, right? So which I think Okay, I think electricity is gone. Let me check. Let me do this. Is electricity gone or someone just turned off the lights? But it's fine. So, when we come to the inverse, yeah, so can you guys still hear me? I think electricity was off for some time. I don't know what happened. Can you guys still hear me? Anyone who can say something, can you still hear me? All right. So if you can still hear me, it's fine. Then now we come to this one of the inverse tangent function. This is the function that is assigned to each real number x, and then the unique number is this. Then we come to this, right? So let's do the proof of this. So now for the arctangent, we're given that the arctan of x, f of x equals to the arctan of x. Then we do the same thing. We introduce tan both sides. So the tan arctan cancels this side, and we're left with x being equals to tan y. We derive both sides. You know that the derivative of tan y is equals to sec squared y times the derivative of y with respect to x, which is equals to 1. We divide both sides by sec squared y. And what do we know from this? We know that sec squared y is equals to 1 plus tan squared y. In this case, this is the same thing as having sec squared y minus tan squared y is equals to 1. You see, right? So this is what you should know. So if I make tan squared y, if I make sec squared y, substitute the formula, tan will go to the other side, right? So this is what you should know always. So this will occur for these intervals. Now check this. What you should know here is that arctan of minus infinity won't be minus infinity. This will be minus pi over 2. And arctan, I think this is something you should know from now, since if you're going to be doing maths next year, advanced calculus, you should know this from here. So the inverse of this will be minus pi over 2. Then the positive one will be pi over 2. You see, even here it's here, where this is undefined, right? So the solution now, one tan y would substitute x, and then we'll have 1 over 1 plus x squared. So this now shows us the derivatives for this, right? What do we get when we have cot, cosec, sec, this one, you see, right? So what we're gonna do, right? Let me highlight this. When we meet on Saturday, this Saturday, we are going to do this, right? These are the ones which we're gonna be doing on Saturday, applying the theorems that we have on top. So we'll do these theorems. I know one of these theorem will come on test 3. One of these will come. We should be prepared for it. So, and also I'd like us to, I don't know, we'll discuss when are we going to have a cross night. I want us to have a cross night where we're gonna be doing or we'll decide, we'll talk about the topics that we're gonna be. I want us to be ahead of the lecturer at least by one chapter, and then we just do questions and prepare for the test 3. I think if we can do that, that will be guaranteed that everyone will understand what's happening in class, and also you'll get more marks. If you know that your product of 90s, I'm sure you're gonna be close to 100. If you know your product of 50s, you're gonna be close to 80s, and so on. Is that right? If we do that, and then we come to this now. They give us, they say that we should find dy over dx if y is equal to the tan of root of x plus 1. You see, right? So what we know from the previous example is that, from the previous theorem, is that if we have y being equal to arctan of y, this would be, first I would introduce tan both sides, and not tan y, man, x inside here. I would introduce tan both sides. This would be x. You see, right? And then I would derive now. You see, right? Now I would derive tan y, which is equal to I derive x. This would give us, the derivative of tan y would be what? Sec squared y times dy over dx, which is equal to 1. And if we divide both sides, we get that this is 1 over sec squared y. So we don't have to do what they did here, right? We can apply that theorem to get to the solution. So this will be simple because you already know what's happening, right? So let's apply that theorem instead of following this formation which they wrote here, because this one doesn't have a format. So we should do something that can be done to every question that comes, that we come across. So we have y. Let me say, they say that 1, they say find dy over dx if y is equal to arctan of root of x plus 1. Now let me copy this and open a new page. And then from here, let me say we can just paste this. Let's just paste this. So we're going to introduce tan both sides. So if I introduce tan both sides, that arctan will cancel all of this. You see, right? Then I'll derive both sides with respect to x. Then this will be sec squared y, which is equal to the derivative of the root of 1, or the root of x plus 1. That will be 1 over 2 x plus 1 minus 1 over 2 times the derivative of the inside. You see, right? And this will be sec squared y is equal to, this would be 1 over 2 root of x plus 1. Then the derivative of that is 1. So, here I forgot to multiply by dy over dx, right? Let me move the space. But it's fine. So this will be dy over dx, which is equal to 1 over, if I divide both sides, I'll have 2 root of x plus 1 and divide by sec squared y. You see, right? And we know that x squared y is equals to 1 plus tan squared y. So we can just come and substitute here. It's 1 over 2 root of x plus 1 into 1 plus tan squared y. And this will be equals to 1 over 2 root of x plus 1. And then this would be 1 plus, we know that tan x is is tan y, right? Tan y is equals to root of x plus 1. So we can just plug root of x plus 1 inside tan. That will be squared. You see, right? And this will be equals to 1 over 2 root of x plus 1. 1 plus x plus 1. Then this will be what? 1 over 2 root of x plus 1, x plus 2. And then that will be our dy over dx. If we check on the other side, it's the same thing. It's a 2 plus x root of x plus 1 on the denominator. And if we check this side, the same thing. It's a 2 plus x root of x plus 1. You see that if we apply the theorem, this becomes simple, right? Do you agree? So every time we come across arc, trig, or the arc functions, the inverse ones, we're just gonna do this. We apply the theorem. So if we apply the theorem, things become simple. They become easy. So I believe when we meet on Saturday, we do questions. Please don't go home. When we meet on Saturday, we're gonna do this. So we come to the second one. We find f prime of x if f of x is equal to root of x squared minus 4 minus 2 arc sec x over 2. They say right. So did we do the theorem for this one? Let me check. Did we do the theorem for this one? Oh, it's here. Yeah. So let me just also preserve this one for Saturday. Let me also preserve this one for the arc. For all these, I'll just put a star there. This one has a chord also. I'll put a star here. Yeah, it means that on Saturday when we meet, we're doing this 1, 2, 3. After doing those, then we apply the theorems here. It will be simple. It will be simpler than what they wrote here, because what they wrote here doesn't necessarily have a structure. So let me see. Yeah. So let's look at the ones which we've done. Then we apply the structure, right? Then here we have this one. We can do here. We can do 1. We do. Let me see. We do this one. We can easily apply what we did. And then this one is simple. You're just gonna cancel out that. You have y is equals to ln x, and then accent in x. Accent. We can do this one. So we can do 1, 4, 7. And then let me start this. Yeah. So looking at the first one, they say y is equal to arctan root of x. So even you should be doing number 1. Number 1 is so simple, you should be doing it. Should be doing number 1. Actually, let me give you this to do them. Since these ones are simple, 1, 4, I can do 7. Now 1 and 4 are simple, you can try this. 1 and 4, try this. You try this. Then let's do this. So let me just do the one which I know that it looks a bit scary. Over 1 plus sine x. Then they say we should find the derivative. So as to find the derivative, we're just going to introduce the sine both sides. Then we'll have this cos of x over 1 plus sine of x. And then I derive both sides with respect to x. This equals to d over dx of cos of x over 1 plus sine of x. We use quotient rule, right, to derive the right hand side. And then the left hand side, we derive sine, we get cos of y times dy over dx, which is equal to, if we come this side, we keep 1 plus sine x, we derive cos, we get minus sine x, minus, we keep cos of x, we derive the denominator, we get cos of x, all over, we square the denominator. So this will be dy over dx is equal to, mirror to get minus sine x minus sine squared x minus cos squared x, all over 1 plus sine x. Is it sine x or sine? Let me check. Oh, this side is sine x, the other side is sine y. That's cos y, and then here we have cos of y. Then this will be equal to minus sine x minus.
Yeah, I think you forgot where the denominator.
Oh, I forgot to square. Oh yeah, I thought I squared it. And then this is a minus sine squared x plus cos squared x, then all over 1 plus sine x squared cos y. So that is just like minus sine x minus 1 all over 1 plus sine x squared cos of y. Then this will be minus 1 plus sine x all over 1 plus sine x squared cos of y. So this is equal to minus 1 over 1 plus sine x cos y. Now let's go back and check what is cos y, what is sine that. So now let's check. We have this. Do we have sine x? Let me see. Okay. For cos, let's focus on cos first. For cos y, this will be equal to the root of 1 minus sine squared y. And sine y is equal to and this is cos x plus this sine y, what it's this, your cos y is root of the root of 1 minus sine squared y. This is equal to minus 1 over 1 plus sine x into 1 minus cos x over 1 plus sine x all squared. You see, right? And then from here, we can say that we can input here. It's fine. We have this. Let me write that first, and then I'll tell you what to do. Was it minus this one or plus? Oh, it's minus. Then this will be equals to, if I put this inside, this will become the root of 1 minus, not 1, become the root of 1 plus sine x. This will be squared if it goes inside the square root. You remember, right? What I've showed you before. 1 minus cos squared over 1 plus sine x squared. You see, right? And then this will be equal to minus 1 over the root of, this will come here and say 1 plus sine x squared minus cos squared x. So check this. The denominator will cancel out if we multiply this by this. The denominator will cancel out, right? And this will be equal to minus 1 over, now I expanded this one, left 1 plus 2 sine squared x plus sine squared, no, not 2 plus sine squared x, 2 sine x plus sine squared x minus cos squared x. You see, right? And then we have this. So let's see what we can get from here. We need to get rid of this. Let me see. This is let me go to the we have that is not sine, it's cos. So that cos, not cos squared, cos 2x is equals to so if I have cos squared x minus sine squared x, I know that this cos squared x is 1 minus 2 is 1 minus sine squared x minus sine squared x, and then this will give us this. Yeah, let me see if I can get something out of this. So we know from the double angles that we have that this is equals to cos squared x minus sine squared x, right? And this will be 1 minus 2 sine squared x, and this will be 2 cos squared x minus 1. So from here we can factor out negative on the denominator. We have 1 plus 2 sine x minus cos squared x minus sine squared x. You see, right? And this will be equal to minus 1 over the root of 1 plus 2 sine x minus that one, cos squared x minus that will give us cos 2x. You see, right? And then now we see that we're going somewhere. Now, if we have this, we know that, let me see if I make this, so with the formula, can have sin x going out. Either way, it's sin y, right? Sin y is equals to this. If I take this other side, I can have sin 1 plus. Here we have a lot of sin x, right? Is also cos x over sin y. Take one to the other side. Sin x is also cos x over 1 minus 1. Sin x minus 1. And then cos 2, this will be that. Okay, let's find like this. So the cos would be 1, 2. I want to try to check if I can try to remove this in this way. Let me exclude this. I'll use this if this one feels right. Without having to factor out. If I have plus, and I made sin x to be cos x over sin y. Let's change everything to cos x over sin y minus 1 squared minus cos squared x. If I factor out the negative here, I'll have minus plus. If it's cos, let me see for the one of cos. If it's cos, I can have 1. I can have sin y times 1 plus sin x. Let me see. For cos x. Always cos x. Where would I need cos x? Cos x. Cos x would be sin y. Yeah, man, I should have done this here. Okay, let me see. I'm trying to find an easier way, right? So I think I should have done this instead of doing that. So I think I should have, the easiest way around would be me to make cos x with the formula from here, which means that I would have sin y times 1 plus cos of x. Then I come back and substitute it here. I think if I would have done that here, then 1 plus sin or that will cancel. So let me do that here, because if I do this, it's gonna be too long. Alright, I don't want to write. I'll end up using a lot of properties that you won't remember when you're writing a test, so it will be useless. So it means that from here I can copy this, write it this side, and then we know that cos x is sin y, and cos x is sin y plus, was it plus? Yeah, sin y plus this one is sin. Yes, and x is this one. So this times this will give us cos x. So now I can have sin y by 1 plus sin x. There on cos means that this will just be equals to minus 1 over 1 plus sin x, the root of 1 minus, on cos I said that I can have sin y times 1 plus sin x. You see, right? All over 1 plus sin x. So let's square this. We realize that this is gonna cancel this, right? And then from here, this will be the shortest. 1 plus sine x times the root of 1 minus sine squared y. And this would be equals to minus 1 over, this would be sine squared, 1 minus sine squared y, that will be cos. So this will be 1 plus sine x. This will be cos squared y, then the root would cancel, squared would have 1 plus sine x cos y. You see, right? Then let's check what is 1 plus sine x. Let's see, 1 plus sine x would be cos x over sine y. Cos x would be also work. Let me see which one can we replace first to get a faster solution. So sine x, 1 plus sine x. The only thing that we'll have to replace, I think, is sine x. Then we can see the cos. Sine x, let me see, sine 1 plus sine x is equal to cos x over sine y. Let me see, so 1 equals 2. Is it like this? Let me check. If we make 1 plus sine x with the formula, we're going to get 1 plus sine x. We're going to get cos x over sine y. Oh, it's cos x over sine y, right? Cos x, yeah. Cos x over sine y. Over sine y. So this would mean that we know that cos y over sine y, that would give us cot y times cos x. Now the idea would be to get rid of this cos x, right? So let me check if there's an easier way. This one is too long because you have to think of an easy way out. So if I make cos x with the formula, we have sine y, 1 plus sine x, 1 plus sine x. What is 1 plus sine x? Let me check. 1 plus sine x would be 1 plus sine x with cos x plus cos y. One, two, three. Cos y, cos y. Cancel this with this. And cos y is 1 plus cos y. Cos y. We have cos y. Cos y, we have it. Get cos y plus sin x cos y, sin x cos y, and then sin x will give us 1 plus sin x will give us 1 plus cos x over let me see. No man, because x would be 1 minus 2. It should be something like this, right? Yeah, but still, this one also, this property won't get us to the solution also. Let me check. And we can use those ones of trigonometry. We're not yet the ones of integration that there. Cos x cos y. The one problem I have is this one. What can I use for cos? Yeah, this one was a bit difficult for this one too, because I don't think I can think of any. These people I don't know, they are playing with electricity. I don't think I can think of any property that can cancel out that cos, unless if I have to come up with another way. Let me see if I have to come up with another way. Unless if we can't, I don't know, let me check, can we get rid of this? Let me check here. I think even this way that I'm gonna think of here, it will just be a short way, but it won't cancel out the cos. Here I could easily replace 1 plus sine, is it sine x, right? 1 plus sine x with cos x over sine y. Cos x over sine y. And this will be cos y. Yeah, this will just be a shorter way also, but it won't cancel out that. Unless if I have to say, that will just be a property. Let me see. That will just be a property. Yeah, this will just be a shorter way to erase this, and then it takes us to this solution without going all these things which I went through. So it will just take us to this part, this one, or is it? Or we'll just take, yeah, you see, it's just a summary to this, but then still, I'm still stuck here on having to remove this. So right, so I think it's still something I'm gonna be stuck here on cancelling the cos x, cause the cot thing for the cot. Now we do, I think this one was old, also force us to go back and do this property for the cot. The cot, cosec, and this one. So yeah, I think we can cancel that one. Yeah, so I'll check this one. I'll try to look for a property that can easily make us get rid of this cos. Because I think the only thing we wish I could do here is, you see, I've derived this side. Using quotient rule on the other side, I managed to get to this part, right? Then I divided both sides by cos this, cos y. Then the cos y came there. And then from here, I substituted 1 plus sine y or sine x with this. I just made this one with the formula. Then I substituted there. And then I got cos x over sine y times cos y. And then now the idea is, how do I cancel this cos x? Yeah, I'll think of that. How do I cancel it out? Yeah. And then The next topic that we have here, it's L'Hopital rule, right? So for L'Hopital rule, this is the simplest. As usual, this is the simplest. I believe that L'Hopital rule is the simplest. So we have many indeterminate forms. So likely I'm gonna teach you all, including those that are. I think we're gonna touch also those a bit of them that are not part of calculus. They're like calculus, the advanced calculus. But these guys like to bring them here. They can just bring them so to make sure that you don't get total. So here usually you focus on these ones. You see, right? These indeterminate forms. But we even have the ones which we have 0 to the exponent 0, infinity to the exponent infinity, 1 to the exponent infinity, and so on. So we can have different types of indeterminate forms, but usually we focus on this two. So the first one is 0 over 0. And then the second one, let me go to the second one. The second one would be infinity over infinity. And then let me check if we have the third one. The third one, 0 times infinity. And then the fourth one is infinity minus infinity. And then we come to, yeah, it's that. I think they're just 4. So now let's go back to the first one. Now, for the first indeterminate form, right? When you come across a question, let me take this. We have the limit as x approaches 2 of, or instead of doing this, when you first come across a question, you first direct substitute. As long as there is a limit included, you direct sub. Then when we direct substituting here, we find that this is what? If we direct substitute x, this is 4 plus 7 minus 10, this is 0 over 0. When you find that this is 0 over 0, you can apply L'Hopital rule. For us to apply L'Hopital rule, we can say that I'm going to derive the numerator and denominator individually. In other words, I must introduce the derivative of the numerator, derivative of the denominator. See when we go to do exercises. Then when I derive the numerator here, I got 2x plus 3. The denominator got 2x. After this, I must plug again. If I plug on the numerator, if I plug 2 on the numerator, I get 7. If I plug on the denominator, I get 4. This is no longer a L'Hopital rule, right? It's no longer indeterminate form. So it means that I can just direct substitute from there. You see, right? So if we come to the second one, we do the same thing. I plug on the numerator, I get 4 minus 3 is 1, and ln of 1 is 0. And the denominator 4 minus 4 is 0. Then now this is satisfying the L'Hopital rule. Now I can derive the numerator and denominator individual, right? And when I derive the numerator, I got 1 over x minus 3. The denominator got 1. Now if I plug there 4 there, I realize that it doesn't give me undetermined anymore. So I can just direct substitute. Right, we come to this one. So I want the ones which you can derive more than once. We come to this, we plug numerator, we get 0, denominator, we get 0. So I derive once. When I derive, I get 6x squared. This, I get 6x squared minus 6x minus 12. So now the denominator gets 6x squared minus 18x plus 12. Now on the numerator, when I plug, I get this is 6 times 4 minus 6 times 2. I think this, let's see what we get. What do we get when we plug on the numerator? Let me use the calculator and see. We get 2 squared 6, 2 minus 12. I get 0 in the numerator. Denominator, I get 0 also. You see, this is indeterminate form again. Then I'm going to introduce the derivative again. You see, that's when we come here. Introduce the derivative again, which is this. Introduce the derivative, then derive individually, numerator and denominator. I derive them individually. Then on the numerator I get 12x minus 6, denominator 12x minus 18. If I plug now here, I no longer get 0. You see, right? I get 18. If I plug here, I get 6. So this is no longer in determinant form. Then I just plug individual. And then on this one, still the numerator I plug 0, I get 0. Denominator I get 0. Then I introduce the derivative. You see, derive the numerator, sin x, you get cos, you get minus 1, 2x. If you plug again, cos of 0 is 1, then 1 minus 1 is 0, 2 times 0 is 0. You see, you introduce the derivative, you derive again individually until you get this. You see, then this is correct. So this would be the first part of 0 over 0. Every time you get 0 over 0, let's try to look at these exercises. We have the first one. Are you guys done with L'Hopital rule in class? Are you guys done with L'Hopital rule?
Yeah, boy.
What are you doing currently? What did you do? Is it yesterday? What did you do yesterday in yesterday's class? Did you start any topic? First, I direct substitute. I realized that I get 0 over 0. Did you guys start any topic? Then I now say that this will be equal to.
No, we didn't start any topic.
Oh, you just finished with this L'Hopital rule, right? Oh. Alright, if it's like that, then it's fine. I introduce this d over dx on both the numerator and denominator. 5 minus 5x. Then this will be equal to the limit as x approaches 1. Derive 3, I get 0, and then this will be minus 3 over, this will be positive, x squared all over minus 5. Let's see what we get when we derive this. And if I derive this, minus 1 x minus 2, this will be 3 over x squared. That's why I got that 3 over x squared there. You see, right? Then now if I plug again, I no longer get 0 over 0. You see, right? That means that this will be 3 over 1 squared over minus 5. This will be equal to 3 over minus 5. I'm sure we agree on this. You see, right? For the first one, this will be 3 marks. Then we'll come to the second one. If I plug infinity, it will be infinity over infinity. Yeah, this one is for infinity over infinity. And then yeah, let's just go to the ones of infinity over infinity. Then now we're here at infinity over infinity. If I plug on the numerator, I get infinity, denominator, I get infinity. This is in determinant form. It means that I must derive individually the numerator and denominator. You see, right? Derive this, I get 2 over 3, then that is 2 over 3, the solution. Then I come to this one, still I get infinity over infinity when I plug. And then we know that we can derive this individually. When I derive the numerator, I get 2x, there are the denominator that remains the same. I plug again, I get infinity over infinity. I derive the numerator, I get 2, there the denominator, I get e to the x. Then when I plug it there, you realize that the denominator is heavier, right? So this will be approaching 0. So this is what you should know always. The limit as x approaches infinity, 1 over e to the x, this will be 0. You see, right? This one you should always know. Or it can be any number on the numerator, it doesn't have to be 1. So, yeah. Now, we come to this one, we plug infinity on your plug 0 on the numerator. Ln of 0 is infinity. So this would give us infinity over. Then 1 over 0 will give us infinity. So this is infinity over infinity. I introduce the derivative on both the numerator and denominator. And then I derive the numerator, I get 1 over x. I derive the denominator, I get minus 1 over 2 x to the minus that. So let's try to derive this and show you. You see, right? Then that will be the derivative of the denominator. That's how we got it. And then for us to arrive here, we just realized that there's something that is acting as both the numerator and denominator, right? So I must come in and multiply by x over x. And the x on top will cancel. I'll have 1. So let me do it here. And then here we'll have 1 over minus 1 over 2. We keep the base and add the exponent, so it's this minus 1 over 2. If I take that on the numerator, get minus 2x 1 over 2. You see, right? And then we get this. So, but if I apply the limit on that x, I get 0. So that is minus 2 times 0 is 0. That's how we got 0 here. You see, right? So now we come to this one and the determined form of 0 times infinity. Always, if you get that you have 0 times infinity or infinity times 0, this tells you you should take one thing to the denominator. So take one thing to the denominator. You see that always if you get this, tells you should take one thing to the denominator. If you take infinity to the denominator, it becomes 0. 0 times infinity is equal to, if I take 0 to the denominator, it should go as 1 over 0. And this is what? Infinity over infinity. If I take infinity to the denominator, it goes as 1 over infinity, and this is what? 0 over 0. You see, right? So it depends to what is it that I'm taking to the denominator. So always we should do this for us to convert our functions to either infinity over infinity or 0 over 0. You see, right? So we get that. Any question? Are we fine? Are we fine? So I think if we are fine, we can we can now move to this. We have evaluate the limit as x approaches 0 of x ln x. So check this. If we plug this, we get that this is 0 times infinity. You see, right? Now I must take one thing to the denominator. And the one that you should take to the denominator, guys, should be the one that is easier to derive. That's why here we took x to the denominator, because it is easier to derive. You see, right? Since x is easier to derive, we take it to the denominator. Then so that when I take it to the denominator, this will become infinity over infinity. You see, right? Then I can apply L'Hopital rule. You see? That's it. Then let's check this one here. This if I plug pi dA, what this will be 0 times infinity. I must take one to the denominator that is easier to derive. And the one that is easier to derive is this one. You see that? So I must take 1 over that. You can take that to the denominator. Or what they did here, they changed this to 1 over cos, which is also another option. Or if you wanted, you could take, you can say sec x over pi minus, not pi minus. You can even say 1 over pi minus 2x. But whatever you take to the denominator, it's either the one on the numerator will decrease or the one on the denominator will decrease. So check something. If I derive this will increase because I'll keep on squaring the denominator. Is that because of quotient rule? If I derive the numerator, it will never change. That one will just change, alternate within itself. So it means that the best option, if you are able to change this function to something, change it. Let's say we're dealing with multiplying by 10 here. We can just use to sine x cos x. Already we have a denominator. You see, right? That will make things super simple. So do we agree? If you have an option to change it to something, you can change it. But if there's no option, you'll always choose the one which is easier to derive and make it a denominator. So let's plug now and check if this is infinity over infinity or 0 over 0. So we have this numerator 0 over denominator, cos of that will be 0. So this is 0 over 0. So you can now derive individually the numerator and denominator. You see, then you get that. And then we have this one of infinity minus infinity. The moment you see infinity minus infinity, it tells you should cross multiply. You see that? If you see infinity minus infinity, you should cross multiply. Should cross multiply. So yeah, do you agree with that? So I think we can stop here now, guys. The other ones I want us to do them contact. I want us to meet for these. I want us to do them contact. So remember, every time you see infinity minus infinity, we cross multiply. Cross this, cross this, cross this, so that it can be in the form of over something, something over something. So we can check after cross multiply. We check whether this is in 0 over 0 or infinity over infinity. So you will see that L'Hopital rule is simple. It's just a matter of how to do the function or to derive and so on. If you know how to derive, you're fine. Are we fine? So I think for this, we will save the exercises. And I also believe that after here, since after L'Hopital rule will be coming to the... Did you guys do the mean value theorem?
No.
All right. I think if they do the mean value theorem, then we'll do this one.
And the L'Hopital in TA, we didn't do L'Hopital rule.
Oh, it means that you are still going there.
Yes.
Oh yeah, it means that you are still going there. At least you'll be on Friday. Friday there's no class, right? It's holiday. You guys must are not going home, ne? Yeah?
We are.
No, guys, you can't go. We have next. We have elementary curve sketching. This one is a bit difficult, so we need time to if we can meet on Saturday, we see what we do. Yeah, I think when are we coming back from this whatever Good Friday? Can't we go? We have money to waste in it.
Tuesday.
But you always want, every time there's something you want to go, or you guys play with money, you must send us that money, please. If you don't know what to do with it, send
We
it
don't
to
live
us.
far.
Eh?
We don't live far.
You don't do what?
Some of us don't live far.
Hey, even if it's 15 rand, you're wasting money. Even if you pay 15 rand or 70 rand, even the 70 rand is worse because it can buy KFC. You see, you're wasting money. Should be buying KFC and staying in your room, study your books, eat, and relax. You're wasting money. So, no problem, guys. Let me end the session here. When we meet, since TA hasn't done Elopita rule, when we meet, we're going